Let's consider statically indeterminate beams now. What is a statically indeterminate beam? Well, it's a beam that you can't solve with statics. So here's a simple one. If we have a load in the center of this beam and supports at either end, you might look at it and say, man, no big deal, I can solve this from statics. No, you can't, because notice that at the end we've got several fasteners that prevent the ends from rotating. Remember, in statics, when you had a beam, it needed to be simply supported and allowed to rotate at either end in order to solve it. So there's too many constraints here. I mean, it's possible that we could have started with the beam being twisted on one and twisted oppositely at the other post, right? There could have been a preload in it. Now, even in what we're about to discover, that preload is not something we could really take into account, but it serves to illustrate the point that these fasteners prevent rotation at either end, and so it's a fixed-ended beam with a load in the center, and so what we have in statics is inadequate in order to calculate the loads or the reactions at the posts, and therefore also the stress and the loads inside of the beam. The deflection curve would look something like this. If the ends simply are not allowed to rotate, intuitively you realize that if you apply a point load in the center is going to deflect, but it's going to come in from the sides straight and then taper off and angle away from the walls, not at the walls. So the deflection curve is really not all that difficult to intuit out. Here's another example of a beam that is statically indeterminate. It's fixed on one end, so it's not allowed to rotate at one end, and it would be cantilevered except it's supported out at the end. So if we didn't have that cantilever, statics could help us solve for the moment back at the wall, but since we have that supporting column, things are a little different, right? Statics can't deal with that extra load. You'll end up with not enough equations and too many unknowns. One of the extra knowns, of course, would be the load in that supporting column. But of course we can build this, right? And then we can put the roof load on top of it and measure the load. So certainly nature figures it out somehow. And the key is to understand that deflection is what helps us, okay? So that's why I keep going back and saying intuitively, here's the curve, the deflection curve, for that loading scenario. So with a simple support out at the end, notice that RB has a line through it indicating that point can't move up and down. That point has to remain where it's at, and that's really the key to solving these statically indeterminate beams. Obviously at the fixed end the beam is not allowed to rotate or translate, so it will remain fixed there, and as you come away from the wall the beam does deflect down, and I think my video is going to be backwards, so I'm sorry my hands are on the wrong sides, but you get the idea. At the wall there's no rotation, no translation. At the simple support on the other side there is rotation but no translation. And that, as I said, that deflection is really important. It gives us the last equation. We could even solve a continuous beam where we have multiple reactions where the beam is not allowed to deflect linearly, but in this case can certainly deflect angularly at those points. We'd have distributed loads, point loads, all sorts of things, and yet we could still solve these statically indeterminate beams. Now there are a couple different ways to do it. There's a direct method which involves Appendix A25. You should go back there, you should mark it now. But basically it's broken up into supported cantilevers, which are cases A through D, beams with fixed supports, cases E through G, and then continuous beams, which are cases H through J. Now again, these are not all the possible types of beams that you could encounter. What's nice about this though is you can still use superposition with these if necessary. Often, and rather what we'll do though is use deflection. Now with the method of superposition, what you can do is consider two separate beams that are simply, they're not statically indeterminate. You can use that and put them together to represent a beam that is statically indeterminate. So we can either go and use the statically indeterminate solutions, or we can actually use the statically determinate solutions. Now how would we use those? Because if the beam is supported out at the end, what does that mean? Well, the end can't deflect, right? So if P applies a load but the end support wasn't there, then point B would deflect by an amount Y sub B1, right? We could calculate that if we knew where P was, what was applied, the properties of the beam, and so forth. But realize that the job of the support is to provide enough load that would make a deflection equal and opposite to YB1. So YB2 would end up being the same amount as YB1. In other words, it would exactly offset it so that point B doesn't actually deflect at all. That's the key here to taking these two, putting them together, and generating from them a statically indeterminate beam. Here's another example where we have a beam on the right that has 3 supports and 2 loads, and we realize that the ends don't move, the center can't move either up and down, but we're going to model this as if that center support was an external load that moves the beam in the center an equal and opposite distance to what the 800-pound loads are going to do. So see YC1 and YC2, the deflection due to the 2 800-pound loads, and the deflection that would be if the center load was by itself, those two sum to 0 because one's down and the other one's up, and they just need to cancel out to represent the actual beam, which is where the center point does not deflect at all. So this is superposition, and it uses statically determinate solutions. There are other methods as well. One is the 3-moment method of distributed loads. Now there's an equation in your book that's pretty long. I'm going to show you 2 of them. I don't have the other one, but I'll show it to you in the context of example problems. But the left-hand side is always the same, and it represents the moment at A, the left-hand side of this beam, the moment at B, which is the moment within the beam in the center above the support at B, and the moment at C. Now in this particular beam, there may or may not be any moment, right? If there was some cantilevered beam out beyond this, then certainly there would be some moment there, or if there's a point moment applied at A or C, then that could add to the moment. That would be the moment at A and C. Now understand that usually in this equation, regardless of its various incarnations, the unknown is usually the moment in the center. In fact, it should always be the moment in the center, the moment at B that is the unknown. The right-hand side of the equation represents the distributed loads between the supports. Okay, so it's very important that you keep all of these symbols straight and you know what they go with. And again, I'm going to work an example problem for you, maybe even a couple, so that you can understand how to use this equation, because actually this is not all there is to it. We can also deal with beams that have concentrated loads, and you see the left-hand side is the same as it was before, but the right-hand side includes the effects of the point loads. Now it turns out we can actually combine these two together, and the left hand side remains the same, but the right hand side would have terms that represent point loads along the length of the beam and terms that represent distributed loads along the length of the beam. It's just that the equation became very unwieldy and I decided not to include it in the PowerPoint presentation, but I'll show it to you in the context of example problems and show you how to use this equation.